terawatt hours, floating wind 870 terawatt hours, plus an additional lump about the same size that's more than 100 nautical miles offshore. Tidal stream 116 terawatt hours, tidal range 26, and wave 40. So a very large practical resource and significant resource across all of the 5 technologies. So as Tim mentioned, we looked at 3 deployment scenarios. And what you see here, if you follow the top line all the way out from 2010 to 2050, this is the deployment path we would need to follow if we were to develop the total practical resource. And we've looked at 3 inflection points along that pathway, the first of which takes us to a position where we can generate 50% of UK electricity from offshore renewables by 2050. The second is the one Tim mentioned. This is where we become a net electricity exporter. We produce, using offshore renewables, the same amount of electricity as we consume in the UK in the year 2050. Now, bearing in mind that the UK only has the ability to absorb part of that resource, we will need to export some of that power. And then the third scenario, which gets us closer to the practical resource, is a net energy producer. This is where we generate from offshore renewables an amount of electricity that is equal to our total energy demand in the UK. So not just electricity, but also any solid or liquid fuels. Certainly. So the upper limit total practical resource gets us to about 530 gigawatts of capacity across the 5 technologies. And that equates to just over 600 terawatt hours. The dark blue line you see at the bottom is currently planned renewable technologies, offshore renewable technologies, of about 50 gigawatts. And so we've selected 3 scenarios that span the range between what's planned today and what we think the total practical resource could be. So fundamental to all of this work is the cost. How much is it going to cost us to deploy each of these technologies? Now, we recognise we were doing the study in a relatively short space of time. There are other people working on very detailed cost studies. So we made some simplifying assumptions. We applied learning rates to the cost today for each of these technologies, and using the deployment over time, that enabled us to estimate costs in 2050. The ranges that you see on each of these cost numbers give you some indication of the degree of uncertainty around this. However, we do see that fixed wind is likely, of the 5 technologies, to have the lowest cost in 2050. And the reason for that is twofold. One is simply it has a head start today, and it benefits heavily from developments in onshore wind. And the second is the size of the resource is significant. If we were to develop the full practical resource around the UK, that gives us an enormous opportunity for learning and bringing the cost down. One thing, levelized cost, this includes not only the cost of building the technologies, but also estimates of the cost of operating, maintaining, and taking away the technologies at the end of their lifetime. So what I'm going to walk you through next on this slide and the following slide is our view of how the resource might be deployed over the next 4 decades. And what you see on this slide is the picture for 2 decades, the 2010s at the top and the 2020s. The x-axis is the total electricity generated in terawatt hours, and the y-axis is the levelized cost. And what you see here, each of these blocks represents a particular site type for each technology. So these dark green blocks here are offshore winds, rounds 1, 2, 3, and the Scottish exclusivity agreements. The width of each of these blocks is the amount of power generated by a particular site type. And so what you see in the 2010s is a development path with mostly fixed wind, but then coming in towards the end of the decade, we've got floating wind, tidal, stream, and also wave power. The picture changes quite significantly when we move into the 2020s. By that point, this white block represents all the capacity that was built and installed in the 2010s. But now we're adding a much larger amount of capacity, and there's a much more diverse mix of technologies coming in. So what we've done here is, in each decade, we've built the cheapest site types, the most economic site types first, and then we've worked through the order of site types, moving gradually into more and more expensive site types. Those might be in deeper water, they might be further offshore. In the 2010s, you'll see there are some higher numbers here for the non-fixed wind technologies. And that's because while these are more expensive than fixed wind sites, we make the assumption that in the same way that in the previous decade we've pushed ahead with the development of offshore wind with fixed foundations, we would do the same for new technologies in order to start bringing them down the learning curve and start gaining a greater understanding of what the costs of these are. And you see that pattern repeated again in the 2020s. There's a big amount of fixed wind here, principally around 3 sites are being built. But then there's also large amounts of floating wind, of tidal stream, of wave, and also of tidal range. So we've got a really broad set of technologies coming in the 2020s and taking us up to about 400 terawatt hours of power. Worth also noting here, while this is a huge deployment, the average build rate across this decade is 8 gigawatts a year. Clearly a huge step up from where we are today, but we felt within the realms of possibility. Moving on to the 2030s and the 2040s. At the top here you have in white all the capacity that was built in the 2010s and also in the 2020s. And then we've got new additions coming on in the 2030s. Again, the cost is coming down because of learning, because we've been installing a lot of capacity already. And the same is true in the 2040s. Again, the cost of the new sites comes down. By this time, we've deployed all our fixed wind sites, so the full fixed wind capacity, and we're moving into other technologies. We're also, on the left-hand side here, this pink area, we've repowered by this stage the original rounds 1, 2, and 3 sites that were built in the 2010s. And this has a significant effect on cost. Whereas the costs here were £100 per megawatt hour plus, when it comes to repowering in the 2040s, these costs come down significantly, and we're now looking at a levelized cost that's more in the region of £60 to £75 per megawatt hour. Yeah. So this takes us up to a total generation of 610 terawatt hours, and this is the second of our 3 scenarios that we laid out. And just one key number, if we were to follow this scenario, that would involve deploying about 20,000 offshore wind turbines around UK waters. So what are some of the main challenges to achieving anything like this level of deployment? Provision of low-cost financing. This will require tens, potentially hundreds of billions of pounds of investment. A small change in the cost of financing will have a huge impact on the cost of that deployment. It's crucial to ensure that there's not only the capacity of the financing sector to finance offshore renewables, but also that the risks are perceived as low and the cost of financing can be reasonable. Managing the variability of this power will also be a major issue. I'll come on to that on the next slide. The grid connections necessary to connect centres of supply and demand will be a huge challenge. Worth noting that in our lowest scenario, all of the power is required for the UK, and therefore we don't need extensive grid connections to Europe. However, some grid connection is likely to be useful for balancing and backup and storage services. But as we move into those higher 2 scenarios from the previous chart, we start to need very large amounts of interconnection with Europe. And that is where we get into one of the key drivers of all of the economics here, is given that we have the ability to produce much more electrical energy than the UK can absorb, one of the key drivers of value will be European demand for this power and the price level at which Europe is willing to pay for this power.